Alright, so last time we saw the analysis for lenses, and we saw the application of thin lens formula, and we saw various questions where there were multiple kind of events involved, including situations where there can be virtual objects created because of various combination of lens and mirror, etc. So continuing with some application problems of that type like we saw last time. So let us start with an example. So this is not an example of thin lens, rather it is an example more about refraction really. So we have a solid glass sphere. So refractive index of glass is the standard value 1.5. And let's say this has a radius of 24 centimeters, like that. Okay. Now, what we are doing in this case is along this particular diameter, so along this particular diameter, which is going to act like a principal axis. Oh, I still have a couple of more people joining in. Yes, just a moment. Yeah, so this is an axis, an imaginary axis, which is passing through the center of curvature of this particular lens, rather this particular sphere. And there is an observer who is viewing from this side, and there is a point object over here. Right, so it turns out that if the point object is kept at a certain distance x over here from this surface, then the final image of it is formed over here at the same distance x. So we have to find the value of x for which this will happen. There is a unique value of x, a unique value of distance which we get in centimeters, at which if we keep the object on one side, for normal line of sight from the other side, you will see a real image exactly at the same distance but on the opposite side. Okay, so for that to happen, how much should we keep the distance x as? That is what this question is about. Just try this out, people. So as you can see in this, you will be applying the fundamental principle of refraction at spherical surface, and obviously you assume that the medium outside is air. Just let me know if you got the answer, anybody, for this. Yes, Shomadik, the answer is correct. Good. Oh, by the way, people, also let me know if there are any questions from the last week's test, geometrical optics part, that you want me to discuss. Or give you some hints, because there is the full detailed solution of the test paper also which you'll be getting. But if you want to try some questions out on the basis of hints, you want some hints, etc. In that case, just let me know about last week test. Okay, anybody else got the answer so far? Somebody has given me the correct answer. So the hint to you people in this is that the only way you will understand this without doing too much lengthy calculation is that the reversibility principle applies. So if you kept the object on this side and the image is on I at the other side, now if you replace the image with the point object, then whatever O is over here should become the image of that. So if the point I in my diagram is actually the object, then the point O should also become the image. So apply the reversibility principle and see if you can simplify your solving. Otherwise, we'll see this question will become too lengthy to handle. Yes, Ashish, that's correct. Okay, so I was telling you, if you utilize the hint which I have given you, which is basically the principle of reversibility of light over here, you understand that. Okay, so what we understand is that a paraxial ray of light going from this point object, so we have an axial ray of light like this, and the final image is over here. Then that beam of light should emerge out like this. Okay. So it should emerge out like this. And the reversibility principle tells us that if we have a beam of light like this, it should emerge out like this. So there should be some symmetry. You know, if this angle is some alpha, then this angle should also become alpha. So in other words, here, if at this point the angle of incidence is some I, at this point, the angle of emergence should also be equal to I. So that is only possible if you have this situation, that the beam of light which is transmitted inside, that should become parallel to the principal axis. this beam should become parallel to the principal axis OI. That is the only logical way in which you can see that this will be symmetrical. So for that, what we have to do is, for the first diffraction, that is from air to glass, the object you take as O, so you take U as minus X, but the image, okay, this should become at infinity. Okay. So V you should take as tending to infinity, because the refracted rays are parallel to principal axis. So make use of this concept, okay, and then solve that refraction. You will get the answer. So you should be getting the answer by solving this way as 48 centimeters. Okay, because this has refractive index of glass as 1.5 given, and the radius of the sphere is 24 centimeters given. So X, which you have to find out, that will come out to this. So I'm just checking your messages. No, Sudhir, to answer your question, what happens is that the Zoom session become very confusing if I allow students all to talk at the same time. So that is why I have given you the option of sending me. I mean, that is why we are keeping the comments as that you can send all your doubts and questions in chat. Okay. You can tell me whatever doubts you are having by chat. I'll explain to you. Because everybody has different internet speeds, and then as students start chatting, my system also starts hanging up, and a lot of confusion and a lot of time that gets wasted as a result of that. So if you are having any doubts during the week in between the two lectures while you are doing homework problems, you don't need to wait for the next lecture to clear your doubt. You can always send me the doubt on WhatsApp, and I'll help you out with it then and there. And while the lecture is happening, whatever doubts are occurring, that you can just send me on chat. I'll help you out. Okay, so just apply this principle now. So for this refraction, air to glass, so refractive index of glass divided by V minus refractive index of air divided by U should be equal to difference in refractive index of glass minus air divided by radius of curvature of this part. Now for the first refraction, this is your pole that you are considering. So this side is negative and this side of it is positive. So you should get 1.5, but by infinity, so it doesn't really matter. Minus 1 by U, which is minus of X, will become 1.5 minus 1 divided by radius, which will be plus of 24 centimeters. So this will give you 1 by X is equal to 1 by 48, or X is equal to 48 centimeters. Now for the second one, you don't need to check because it's just a reversibility principle. But if you want, you can check, you will get this as this one. Okay? So for the second refraction, you can automatically see that what is happening for the second refraction is that inside the glass, firstly the refraction is happening from glass to air, and you have your incident beam. It's coming like this. parallel to the principal axis. So if this is your point of incidence, it will bend away from the normal, and it's somewhere here, and you'll be able to see that that will automatically become equal to the value of x that we got earlier. Now if you apply the refraction to for glass to air, okay, where you take the object distance at infinity, because that's what's happening over here. So that is the solution of this question. Okay, students, I'm just having some internet speed issue. Just give me a moment. I need to. Give me a second. Yeah. So in the previous question, just coming back for a moment here, we don't actually need to check the second refraction. We know that this will give us the object image distance as x only, because here what is happening, that the refraction is happening from glass to air, and the object distance we have to substitute as infinity, because the incident ray is parallel to the principal axis. So keeping that in mind, we'll get refractive index of air divided by V minus refractive index of glass divided by infinity is refractive index of air minus refractive index of glass divided by radius, which will be minus 24 centimeters here, because the center of curvature is here. This is the pole. This will consider as the negative side. This will consider as the positive side. So when we solve this, naturally you can see, you will get that 1 by V is equal to 1 minus 1.5 by minus 24, which will tell you V is plus 48, which is nothing but V is equal to positive of X. So this calculation here was unnecessary. You could have just understood this from the principle of reversibility. Okay. Now the thing is, without using this principle of reversibility, your solution here becomes very complicated, okay? Because you have to take some image at a hypothetical position x1 and then calculate diameter minus x1 and take that as the object distance and all, and you'll see that the calculation becomes way too lengthy. So the better way of doing it is by understanding the reversibility of light symmetry over here and working it out. Okay. So now let's quickly look at the calculation of the next question which I've given you. So this example was, we have a convex concave lens which has radii 12 centimeters and 18 centimeters. So first of all, and refractive index of glass as 1.5. So first of all, let's calculate the focal length from that. So as I've discussed earlier, it doesn't matter whether you're keeping the concave or convex lens like this or like this. The focal length will be the same in all cases. So for light incident from this side, 1 upon f will be equal to refractive index of glass minus 1 into 1 by r1. Now here you can see this side will be the first surface, and this side will have the smaller radius. This will have a radius of, in this case, 12 centimeters, and this side will have the larger radius like this. It will have the radius of 18 centimeters. So this will become 1 by r1, which will be 1 by plus 12, minus 1 by r2, which is 1 by plus 18. Okay. So as you can see, your focal length will become 0.5 into b minus 2 by 36. So your focal length is becoming plus 72 centimeters. So that means it is a converging lens of focal length 72 centimeters. Okay. So now you keep that in mind, that there is a converging lens of focal length 72 centimeters, which is obvious. Okay. Now it doesn't matter which side you kept the object in, but whether the object is kept over here or it's kept on that side, we can look at the image formation by understanding that if this distance is 32 centimeters, then it is actually between focal position on this side, or the image of the focal position and pole. So we know that this will give us a virtual image. We know from our analysis that this kind of a situation will give us a virtual image, because these rays still come out divergent. So we know that these rays have to be produced back and they form a virtual image somewhere. So this is where analysis also helps. We can, sort of estimate what is happening. But anyways, here, so 1 by v minus 1 by u, which is this, will be equal to 1 by f, which is 1 by 72. So as you can see, 1 by v will become 1 by 72 minus 1 by 32. So v will become minus of 8 into 36 by 5. That is minus of minus of 57.6. Okay, so this kind of situation. This was the other example. Okay, now next up. Okay, so people hope this is done. This is clear. Okay, next up, let's do an example involving relative motion in the case of a lens. So for relative motion, in a situation with a lens, we again use the same kind of principle that we have earlier understood for spherical mirrors. That if, let's say, this is the position of the object and this is the position of the image, and this distance is x and this distance is y. So we have 1 by v minus 1 by u is equal to 1 by f, or when we substitute this with sign convention, we get 1 by y minus 1 by minus x is equal to 1 by f. Okay. Now we have a situation where the object is moving like this. Okay. It's moving with a velocity ux like this, parallel to the principal axis. Okay. Then we'll understand that the image will start moving like this with a velocity vx. Sorry, vx only we can say. Okay. Such that ux in the diagram you can see is minus of dx by dt. Is the rate at which x is decreasing with time, and vx similarly is the rate at which y is decreasing with time. If I take vx like this, okay. So Whereas if the lens is stationary, so in this what is happening? F is constant. Focal length is not changing. The focal position is not changing, but x and y are changing according to this formula. So x and y are variable quantities, whereas the focal length is a constant quantity. So what we do is you differentiate this equation. So differentiate with respect to time. So you get differentiation of 1 by y plus 1 by x is differentiation of 1 by f, which is by the way constant. So we get minus 1 by y square dy by dt minus 1 by x square dx by dt is equal to 0. So you get this relation over here that dy by dt becomes minus of y by x ka whole square times dx by dt. So dy by dt for me over there was minus of vy, dx by dt was minus of vx. So the minus signs you can say cancels off, and this becomes magnification square times. Rather, this was vx, this was ux. Okay, so this also tells me that in this above diagram, if x is decreasing, then y will be increasing. Okay, so this in fact tells me that if x is decreasing, it implies that y will be increasing instead. Or if x is increasing, then y will decrease, but at this kind of. Okay. And of course, magnification you will calculate by the UV formula again. So this is the principle that happens, that we apply for relative motion along the principal axis, or parallel to the principal axis. The velocity of the image parallel to principal axis just becomes magnitude wise m square times the velocity of the object parallel to principal axis. This is the general rule of thumb, and this is the same as in case of mirror. Same thing, exactly the same. Only the formula you'll use for finding UV and from that magnification, that is different. There for mirror it is 1 by v plus 1 by u is 1 by f. Here it is 1 by v minus 1 by u is 1 by f. That is the only difference. Otherwise it's one in the same thing. You understood this now? Now likewise, if you are having, so this is when there is relative motion parallel to the principal axis. Now likewise, if you are having relative motion perpendicular to the principal axis, okay, then also it's exactly like we had discussed over there. Okay. If we have an object which is now moving like this, it's moving with a velocity perpendicular to the principal axis uy like this. So this is where it is at t equal to 0. Okay. Now let's say after some time it reaches over here. It reaches O prime at t equal to delta t. Okay. Now supposing this object was such that it's the focal position is somewhere here, so its image is real, okay, and it's somewhere here. So at the time when the object was on the principal axis, at that point of time the image you would have got would have been somewhere here. This would have been the image, let's say at t equal to 0. But by the time the object has gone over here, where will the image be located? The image will be located somewhere here. It will be located at I prime at t equal to delta t. And if you were to find the position of this image, you would treat this like an extended object and treat this like an extended image. So this distance, okay, if O prime has a height of h, and on the other side I prime has a height of h prime, then you can see that h prime upon h is nothing but the magnification factor with the sign convention. which by the way is v by u. Okay, so now you can see in this diagram, O prime is nothing but the distance moved by the object with this perpendicular velocity in time delta t. So this is u by into delta t. And during that time, if the image has developed a velocity like this of Vy, then this height's magnitude is nothing but Vy into delta t. So again, you can see that h prime upon h, which is the magnification factor, is actually nothing but Vy upon Uy. So this becomes. So the other concept here becomes that velocity of the image perpendicular to principal axis. Okay, is nothing but magnification times velocity of the object perpendicular to principal axis. Okay, and this formula you can even understand with the sign of m. So if m is negative, then they are going in opposite directions because it's a case of real object giving you real image, that kind of situation. So here m is with sign. Whereas suppose we had a case of real virtual like this one. Suppose we had a case like this, that a point object somewhere over here is giving you a point image somewhere over here. Now if the point object starts moving like this with the velocity like this, here the point image will start moving like this, and here the magnification will be a positive quantity. Okay, so that is why velocity of image has same sign as velocity of object. Okay, this is perpendicular to principal axis. Whereas when it's parallel, then it's a factor of m square, and because m square is not giving you any sign, so you're just understanding that as a relationship between the magnitude of the object's velocity and the magnitude of the image's velocity. The direction you have to figure out yourself, and that's where again the analysis helps. You know that if the object is moving towards the pole where the image is moving, or if the object is moving away from the pole, which direction the image is moving, so that you can work out manually. So this is the full analysis of the two components of velocity that a point object can have, parallel to the principal axis and perpendicular to the principal axis. So again, this is basically same as in the case of mirror. Both the formulae are same as in the case of mirror. Okay, so people hope this is clear, both the derivation and the final formula, okay, how it applies. Okay, so now let us see some kind of questions which are very interesting to solve with this particular concept. Okay, because the question is given in such a way that the information is kind of it's partial information given to you in the question, and you have to decipher what the question is actually trying to say. So let's pick up a question like this. So we have a diverging lens. It has a focal length of, let us say, 6 meters or 60 centimeters. And the lens is fixed. And let's say we have a person on this side who's also stationary. But on this side, there's a vehicle coming in this sort of direction. So let us say, now the person, the man, observes an image, observes the vehicle to be 1/3 in its actual size in terms of the height of the vehicle. Okay. He's seeing the size in terms of the height, not in terms of the depth. So he's observing this height, this vertical height, and it appears to be 1/3 the real size. Okay, and coming towards him at a speed of, let's say, 4.8 meters per second through the lens. This is what the person is observing. That the man observes the vehicle to be 1/3 of its actual size, and he observes it to be coming at him at 4.8 meters per second as he's seeing it through the lens. So you have to find the actual position of the vehicle with respect to the lens at this moment, when it appears to be like this, and the actual velocity, say VO, of the vehicle. Okay. Yeah, so just minimizing this and try this out yourself. Oh, we will just one thing over here. Make a small correction. Make this focal length as 60 centimeters instead of 6. Okay. I mean, you can still solve it for 6. There's no problem. But practically, the question will become a little wrong because the vehicle's own dimensions are going to be few meters now. So if you take the lens's focal length as 6 meters, then it's not going to be a case of paraxial rays. The vehicle's own height might be something like 2.5 meters or something like that. So it's not receiving paraxial rays. So then the actual application of the formula will not coincide with the experimental observation. So let's assume that the vehicle's own size is negligible compared to the this thing. Okay, so assume the size of the vehicle, or if we had taken 6 meters, then we should have thought of it like a toy vehicle, which is just a few centimeters in size. Okay, so assume the size of the vehicle is very small, is negligible compared to the focal length, so that we can still apply the the paraxial rays formula that we're using, that is the UV formula and the magnification formula. Yeah, so this should be fairly simple. I'm just verifying your answers. The actual position of the Ganesh. Yes. So the vehicle's actual velocity will become 9 times 4.8. And yes, the position will become 120. That's correct. So 9 into 4.8 is how much? Yes, 43.2 is correct. Okay, so with our background of diverging lenses in place, it's not difficult for us to understand here that as we are seeing an extended object, like this, let's say, we are observing it through this lens, its image will appear to be somewhere over here, between its focal point and pole. And if this distance is x and this distance is y, the magnification factor is going to be y by x. Now this is given to be 1 by 3. That means y is equal to 1 by 3 of x. So we have 1 by v minus 1 by u is equal to 1 by f. Now with proper sign convention, v over here will become minus of x by 3 using this value. And it will become minus of x. And the focal length was given to us as minus of 60 with proper sign convention. So we're getting 1 by x minus 3 by x minus 1 by 60. So x will become 120. Okay. And also we will see that if the object is moving with a velocity VO like this, in the image here will be moving with a velocity VI like this. Okay. And that we know from our analysis that as the object is moving towards the pole, the image which is virtual here will also be moving towards the pole. So we know that from our analysis of diverging lines. For a diverging lens, if the object is approaching the pole, then the image, which is the virtual upright and diminished image, between focal point and pole also approaches the pole. That is like that. So here V of the image will be m square times V of that. So in this, m is given to us as 1 by 3. And V of the image is given to us as 4.8 meters per second. These two things are given. So speed of the object we will see. That should be the time. So this type of indirect information given and application of that becomes important. Now another thing that can be asked for you is that will the image appear to be, I mean, to him when he sees through the lens, will the object appear increasing or decreasing in size as he sees it through the lens. As he's seeing it through the lens, will the size of the object appear to be increasing or will it appear to be decreasing? So for that, we have to understand what is happening to the magnification. As the object is moving towards the pole, the image is also moving towards the pole. But is the amount of magnification, is obviously a diminished image, but is the value of the magnification factor, and that is some fraction, is it actually increasing or is it decreasing? If it is decreasing, then the size will appear to be dropping. If it is the magnification factor is increasing, then the size will appear to be increasing. So think about this carefully. Yes, Uday, your answer is correct. Ganesh, just rethink once. Okay, just think about this and tell me this in sense. Moment I will refresh the screen, but in the meantime I'll tell you the logic. So what is happening is, as an object moves towards the pole of a diverging lens, the image also moves towards the pole, and the magnification factor actually starts increasing. The further away the object is, the more the diminished the image is, and by the time the object actually reaches the pole, the image is also right at the pole, okay, alongside the lens, and that is when the magnification factor actually becomes +1. So, let's say if at a large distance, the magnification factor is plus 1 by 4, then as the distance decreases, it will change from 1 by 4 to 1 by 3 to 1 by 2, to like that. And eventually it will become 1 by the time the object is very close to the pole. So that is the principle you have to understand over here. So as the object is moving towards the pole, the image is also moving towards the pole, but they are moving at different rates. So the object will end up covering more distance compared to the image. So your V by U factor will always be a fraction less than 1, but that fraction will be increasing as the object is moving towards the pole. So if that fraction is increasing, that means the magnification factor is increasing. So that means the size of the image seen is actually increasing. So that is why the answer to the last part over here will be that it is increasing. Okay, so just a moment, I will continue. Okay, so that is why the last part's answer should be a little bit increasing. So basically you understand like this, that what happens for diverging lenses, let's say initially the object is over here and its image is somewhere over here, E prime, B prime. Now compare that with another object of the same size but closer, so CD. Now its image will be closer. So you might say, okay, if the image distance is becoming less, how come the size of the image is becoming more? But that is because that is the ratio of this and this. So if this is U1 or rather U2, let's say, and this is V2, and in comparison, this was U1 and this was V1. You will see that if U1 is greater than U2, that will always imply that V1 by U1 will actually become less than V2 by U2. Or the magnification for the first one will be less than the magnification. So that is why over here, if the object is moving towards the pole, okay, the diminished image moving towards the pole appears to be increasing in size. Yes. So this is an additional concept which is important to me. Alright people, so hope this is clear. Now another related type of problem we'll discuss is this next one. Like this. Let's see, it has a focal length of 45 meters. Now, the object which I've kept is this kind of an object. It's a U-shaped object, such that this distance is x, and this thickness is b, and this height is h. So given that x is equal to 60 meters and h is equal to b is equal to, let us say, 5 millimeters. Find the position of the image and draw its shape in the diagram. And find the size of the image. So try this out. It's a converging lens, and the object distance is between focal length and double of focal length. So you should actually get a magnified real image, not a diminished real image. So your image distance should come out to be more than 60 on the opposite side. In fact, it should come out to be more than 90 because 2f is equal to 90. Just check sign convention or something, might have made a mistake. Yes, Bhumik, that is correct. Ashish, let me just check the calculation that you have sent me. Just a moment. Yes. Yes, that is correct. Yes, Ganesh, you got it correct now. Ashish, your all the parts are correct of the answer. The size, shape, as well as the position. Okay, so since we have an extended object, we have to develop some slightly more exact way of how we are expressing this. So let us say this object's, this corner point is E, this corner point is B, this corner point is C, and this corner point is D. So our U-shaped object is basically like this. Okay. Now, what we will start with is the image for the point B. So, for the point B on the object, the point B actually acts like a point object on the principal axis. At an object distance of minus 60 meters, focal length is plus 45. So you will get, by substituting, you will get the B as plus 180. Okay. So coming back to the diagram now, just that point B's image will be somewhere over here. Let's say B prime, where this distance, suppose it is Y, that Y will come out to be 180 meters in my diagram. Okay. Now that is where B is located. Now therefore you will understand that C's image will be located somewhere here, C prime. And just as in this diagram, you can take that thickness D as a small change in X. So you can treat this thickness D as a small change in X. So this apparent thickness that you are getting over here of the image, D prime, let's say, that will become delta 1. So that is the concept you can use. So the image of that horizontal bar, BC over there, will become a horizontal bar D prime, C prime over here. And you can find it this way. So see that since we have 1 by B minus 1 by U is equal to 1 by F. So we have minus 1 by Y square dy minus 1 by X square dx. You can see the relationship between delta Y and delta X. Delta Y is equal to minus of magnification square times delta X. And from this, we can also see that the magnification factor will come out to be minus of 3. Okay. So delta Y should be minus 9 times delta X. In fact, it tells you that since it's minus, therefore this is wrong. C's image will not be there. C's image will be in fact on this side. Okay. So in fact, this tells you that delta y being a negative quantity, or you can also understand this logically. If you had a point object that was going from B towards C, the image would be coming back from B prime towards the point. So my C prime should be here. So this should become the image of that bar, B prime C. So this thing B prime will be treated as a delta 1. So this should become, so that distance D prime become 9 times. How much was D now? 5. So it should become 4.5 centimeters. Utna zyada magnify ho jayega. So you know, it's like if you keep a horizontal bar on the principal axis like this, where this is 5 millimeter and this distance is 60 meters. तो ये मेरा extended object है, तो यहाँ पे image कैसा बन जाएगा? ऐसा बन जाएगा. The image will be, if these points are C and B, so here this will be C prime and this will be B prime, and this distance was 180 meters, and this will come out to be 4.5 centimeters or 45 millimeters in size. This is what this is telling you. Okay. Now, likewise, you try to figure out the images for the other 2 points on the corners. The points, my diagram E and D, ये जो points है. So object ऐसा था. So now I have just shown you the image of this part, which was DC. But now also think of the image of this part, EB, or the image of this part, CD. So you realize that this will be like this. This will be like this. And you will also realize that C prime D prime will be slightly less than. It's almost equal to E prime D prime, but C prime D prime will be less. In height. So the shape also gets a bit distorted for the image. Okay, so you can also understand that A prime B prime will be magnification times EB. So it will become minus of 3 times 5 millimeters. Okay. So that is why we had a rod like this, EB. Its image on the other side is like this. So this is 15 millimeters because this is 5 millimeters. 60. Now similarly, this part of the rod, BC, its image is here now, like this. B prime C prime, which is 45 mm or 4.5. And now finally, this part, this is also 5 millimeter. This is also 5 millimeter. This one's image will be ever so slightly smaller than this, almost equal, but छोटा सा change in magnification. This will be nearly 15 millimeters. And this distance is 180 meters. That's here. This distance is 60 meters. Okay. So, you can be asked conceptual things like this also, that, does the shape change? Yes, it changes. It goes from, it looks like 3 sides of a square frame. Now it's like 3 sides of a rectangle, and that too, one side is slightly shorter compared to the other. That one. Also, where the individual sides go. So it's like even like a lateral inversion, along with a vertical inversion. It's also lateral inversion. Because you can see BC right to left and C prime, V prime left to right. That orientation has also changed for the image. So another way to understand the application of this is, for example, if this was a spherical body, here the image will not appear to be spherical. The image will become distorted because the vertical diameter of the sphere and the horizontal diameter of the sphere will get magnified by different factors. But the horizontal diameter will get magnified by a factor of m square. The vertical diameter will get magnified by a factor of m. So it's becoming like a distorted kind of spherical surface, not exactly ellipsoidal, because there's no reason for it to, have the equation of an ellipsoid. But yes, it will look like a distorted sphere. So in general, this kind of phenomena is called the aberration, spherical aberration due to lenses. That not only the dimension but also the size of the images formed. Sorry, not only the dimension and size but also the shape of the images formed are distorted. Alright, so this is an important aspect of the understanding of lens and mirror. Yes, so Somidev, to answer your question, we can get the delta y by doing this also. For the image of C prime D prime, we can do also like this, that take the object as CD. But you'll see it's a very tricky calculation, no? Because then we'll have to take the object distance for CD as how much? It's 60 meters plus 5 millimeters. So it is going to become 60.05. Sorry, 0.005. Because it's not 5 centimeters. We'll have to take U as, you can see it's unnecessary. We'll have to take this as this. Okay. So the image C prime D prime V we have to calculate, and then we have to do this calculation that 1 by V minus of 1 by minus 60.005 is equal to 1 upon plus of 45, and we have to assume that we've done the measurement of all this up to millimeter. So the least count for our system should be at least 1 millimeter, so that we are able to. So then we can find V for this, and from that we can find the difference in the V for C prime D prime with respect to the V for EV. But as you can see, this is a unnecessarily lengthy calculation. In any case, for doing this calculation, we'll then have to apply some binomial approximation, etc. So that's why, because that distance BC is actually very small. That distance BC is very, very small compared to the distance B to the pole. So that is why, since we are taking this as Y, we are able to treat this as a small delta. So it's basically again a mathematical trick that we're using to solve this. Okay. So while you can use this method, but this will become very, very lengthy in terms of calculation. Okay. Right. So that is this part. Now let's move on to the next part of analysis of lenses. So we'll discuss about thin lenses in contact. So we have this situation that not only they are in contact, but in this case I'm taking it as if their principal axis is coinciding. So they have almost a common pole like this. So an object kept over here, you can find its image somewhere over here, whatever. So if the first one has focal length f1 and the second one has focal length f2. So we have for refraction by the first lens. Let's say this is the object O, this is the final image I. We'll take the object as O, the image as some I1. So we'll take the object distance as U, whatever this is. Okay. The image distance we'll take as V1, the position of the image, and the lens is of focal length F1. So F1. So we have the formula for the position of the first image. 1 by V1 minus 1 by U is equal to 1 by F1. That's it. Now what is happening is, basically what's happening over here is that this is the first lens, this is the object. And this would have formed an image somewhere here. This would have been our I1, for which we have used this formula. Okay. But this is actually not happening, because these rays are not reaching here. Instead, actually what is happening, the second refraction or the second lenses thing is happening this way. The effect of the second lens is that these rays emerging out from this, which was supposed to go and meet at I1, but they are now incident on the second lens. So in my diagram, because I1 is a real image for the first lens, it becomes a virtual object for the second one. Whereas if the first lens had been diverging, so I1 would have been a virtual image on this side. So the rays would have become a real image, real object incidence for the second lens. Okay. But anyway, so for the second lens, I1 is the object. And further converge and give you an image over here. So this becomes the final image. And I is the image. It becomes the final image. Okay. So we will take U as actually V1. And our sign convention is same. So we don't need to put plus minus over here. Whatever the sign of V1 coming out from the first formula, that will become the U in the second. Okay. So for the second lens, I1 is the object. And I is the image. So we will take U as actually V1. And our sign convention is same. So we don't need to put plus minus over here. Whatever the sign of V1 coming out from the first formula, that will become the U in the second. Just so in our first formula, if V1 was coming out to be positive, then we will substitute V1 as a positive quantity here and it will represent a virtual object for the second case. If in our first formula V1 was coming out to be a negative quantity because these diverge, then that would be a virtual image over there, but that would become a real object over here. So we'll substitute V1 with the same sign. So there's no change. Whatever V1 is coming with whatever sign from the first formula will be substituted as the object position for the second one. And the image position becomes what we are calculating. And obviously the second lens has focal length f2. So the formula here becomes 1 by v, which is the final image position, minus 1 by u, which is v1, is equal to 1 by f2. And again, f1 and f2 are substituted with their signs. This becomes the second formula. And now if you just compare the two formula, you can see adding them will get rid of v1. Add the first and second formula and you will get rid of v1. And we just have the equivalent lens formula for the combination. That is 1 by v minus 1 by u will become the sum of 1 by f1 plus 1 by f2. That is the final step. So equation 1 plus equation 2 plus 1 by v minus 1 by u is equal to 1 by f1 plus 1 by. Or you can say that 1 upon f equivalent is equal to 1 by f1 plus 1 by f2. But remember, f1 and f2 have to be substituted. Yeah, I'm explaining the second relation again. Second relation में तो क्या हो रहा है? जो first lens ने जो image बनाया था I1, वही image आपका object बन जाएगा. For the second lens, is the rays which are emerging out of the first lens, which would have otherwise formed the image over here at I1. Those rays are becoming the incident rays on this lens. So that object, I mean that image I1 is actually becoming the object. I1 is becoming the object, and I2 or I is the final image. Okay. So here you can see that if V1 is a positive quantity, then it is a real image for the first lens and it becomes a virtual object for the second one. So the sign convention reflects that. First वाले के लिए V1 क्या है? It is the image distance. So if V1 is positive, it means it's a real image. But second वाले के लिए what is V1? V1 is u. So V1 being negative means it's a virtual object. I mean V1 being positive means it's a virtual object. Whereas if on the other hand, if V1 came out to be negative because the first one was a diverging lens, that means the first lens is giving us a virtual image. Virtual image for first lens. Okay. But in that case, what is happening here is like this. The first lens must be diverging in nature. So these rays are going like this and giving you I1 over here. Now, these rays only are incident on the second one. So if these rays are incident on the second lens, they represent what kind of object? Real object. So this I1, and then whatever happens, these might come out like this, these might come out converging, whatever. But so this virtual image for the first lens will become a real object for second lens. So for the second lens, U will become a negative one. For the first lens, V is a negative one. So this V1 being negative implies this, whereas V1 being positive implies this. So for either of the two cases, it doesn't matter whether the first formula gives us v1 positive or negative. Whatever that v1, we substitute that v1 only as the object distance or the object position for the second lens. Sign convention takes care of whether it is real or not, and we get the second. That 1 by v minus 1 by u, but u is replaced with v1. Which v1 we have calculated from the first formula. That is equal to 1 by f, where f is. So now if you add the two equations, you get this formula, which is telling you that the equivalent focal length of the combination becomes such that 1 by f equivalent is equal to. So for formula like this, we define a quantity called power of a lens. It is just defined as 1 upon focal length. And power is technically used by opticians. Power is measured in a unit called diopters, where 1 diopter is 1 meter inverse. So anyway, we can also express this in terms of power, that the equivalent power of two lenses which are in contact with each other is the sum of their individual powers. Okay, so hope this is clear. I'll just take you through the whole derivation once more from the top. So any arbitrary object that we kept here, in the diagram I have shown point object, but you can extend the idea to extended object. Through the first lens, it will give you this kind of situation. Through the second lens, it will give you the situation which is given by the second formula, where the image for the first lens becomes the object for the second. The image formed by the first event, which is refraction by the first lens itself, becomes the object for the second lens. And the image for the second lens becomes nothing but the final image. That's how we are getting the equations 1 and 2. Okay, so Sudhir, hope this is clear to you. Good. Okay, so that is the advantage of Cartesian sign convention, because we then don't have to change any sign when we are substituting v1 from here. If v1 is a real image here, with its sign only it's substituted here, and it represents a virtual object for the second one. If v1 is giving us a virtual image for the first one, with its sign only here, it now represents a real object. Those are the two cases which are possible. So this becomes the formula, and also the equivalent magnification. So for extended objects, also extended objects, the net magnification becomes a product of the magnification by that first. So that is nothing but v1 by u into g by v1. That is nothing but v by v. Where this v and u will calculate by which formula? By the equivalent formula. That 1 by v minus 1 by u is equal to 1 upon f equivalent. This and f equivalent is such that it is 1 by f1 plus 1 by f. So whether it's the magnification formula or is the UV formula, you can just replace the combination of the two thin lenses with a single lens which has this much equivalent focal length. That becomes the whole idea. When two thin lenses are in contact, you can just replace them with a single equivalent thin lens which will have a focal length like this. Understood this now? So let's look at a quick question based on this. Now we will go back to a question we had done earlier actually, and we'll see another way of doing this question. So this is a plane mirror, and so we have a concavo-convex lens, which has radii, say 12 centimeters and 18 centimeters, the values we used earlier today, and refractive index of glass is 1.5, so the same one. But now we have also poured some water on it. So this is water. Refractive index of water will take as 1.3, 4/3. And now what we want to do is, we want to keep a point object on this vertical axis, or rather a point source of light on this vertical axis at such a position that the final image coincides with the object. You must have guessed the situation. Now we want to keep a point source such that, so now also here, assume both the thickness of the glass lens and the thickness of the water layer on top of it are negligible compared to the radii. So they're negligible. They're maybe a millimeter or so, something like that. So we have to find the distance es equal to whatever d at which a point source s should be placed so that the final image coincides with the object. With the source itself. Okay, so we want basically reversal of the rays. Whatever rays the source is emanating, yeah, Ganesh, I will just check your answer. So again, it is a case of the rays have to retrace their path. The reflected rays have to retrace the path of the incident rays on the mirror, and the rest of the rays also have to retrace their path. That means the incidence at the mirror has to be a normal incidence, and it's a plane mirror. Let's add this to your diagram. So that So typically what we want here, yeah, I think Somadeep, your answer is correct. Ganesh, you will have to check your calculation. So the situation we are looking at should be something like this. That you consider any incident ray from the source. It will now undergo fractions. Let's say it bends like this, further like this, and then when it emerges out here, it should emerge like this so that it is parallel to the principal axis. I mean, yeah, parallel to the principal axis. No, Bhumik will have to check your calculation. This should happen. Now, this one should retrace its path. So then these will also retrace their path. Then this will also retrace their path. So that means the rays incident on the mirror should be parallel to the principal axis. Then the rest of the system just replaces this. So that means if we just look at what is happening here alone, what is just happening to the combination of lenses is this. That any ray of light from the source incident on this is emerging out parallel to the principal axis. This is what should be happening. Then only if we keep a plane mirror over here, it will intercept that light and make it retrace its path. So the easy way of solving this now is that replace this combination with an equivalent mass. So if we replace this combination with an equivalent single thin lens, okay, of focal length f equivalent, then we know that where should the point source be placed? It should be at its focal position. Yes, Bhumik, correct. So now we know that this should be at the focal position. So while we can also solve it, by using two events, because before these rays emerge out parallel to the principal axis, there are two events. There's refraction from air to water, water to glass, or three events: air to water, water to glass, and then glass to air. Okay, and then they emerge out parallel. But we can also solve it by this equivalent method. So this should be at the equivalent focal position. So that will be the easy way. We change it into an equivalent system. So that is the approach we'll take over. Okay, so we will treat this thing as a combination of a thin glass lens and water lens in contact. And you'll understand that that combination is like this. This is your glass lens. This is your water lens. So the water lens is, or rather the thin layer of water is forming a plano-convex lens. And the glass is forming a convexo concave lens. And doesn't matter that they're in no air in between. You use 1.5 and the radii are this side is going to be the smaller one, 12 centimeters, and this side is going to be the larger one, 15 centimeters. Whereas this will be, one side will be plain, and so refractive index of water 4 by 3. So first what we'll do is you calculate the focal length of the water lens. 4 by 3 minus 1. 1 by R1 minus 1 by R2. This will become 1 upon 1 by 3 into 1 by 18. So that is, so the water and lens acts like a converging lens of focal length 54 centimeters. Of power 1 by 54 centimeters. Similarly, the glass lens on its own one by R1 minus 1 by R, it's 6 common. Right? This becomes like a glass 6 inches. So convergence. Going to act like this. So the combination acts such that the equivalent power is equal to power of the water lens plus power of the glass lens. So 1 upon F equivalent should be 1 upon 54, all with plus sign, remember, because both of them are plus 1 upon. 18 common. So 1 by 3 plus 1 by 4. Well, okay. So yeah, I think I'm back online now. Yeah, are you getting the audio from me? I don't think so. Yeah, Ganesh, that's correct. Sorry, I made the wrong calculation. Equivalent focal length. I don't know at which point of time we lost the. We did the individual calculation of focal length of the glass lens and the water lens using the lens maker's formula. So if we just had the water lens alone, we would have had this focal length. This one is this. If we just had the glass lens alone, this would have given a focal length. So when we have the combination, we are getting an equivalent focal length from this. So that means that combination of that convexo-concave lens with that thin layer of water above it can be replaced with a single lens, which is of focal length this much. So that means we can replace the combination of the glass and water can be replaced with a single equivalent thin lens, which should be converging length because it's coming focal length is coming positive with a single equivalent thin lens. Of equivalent focal length 30.85 centimeters converging. So now we are up to this diagram. We have understood what to do over here. This equivalent focal length is how much? So that we got. Okay. So coming back here now, we understand that these rays should emerge parallel so that now this thing will reflect it back. So we should keep our source of light where we should keep our source of light at a distance. Suppose this is x. That distance x at which we should keep it should be equal to this equivalent. So that this whole series of events happens. So that what happens. What happens is actually this. Alright, so hope the concept is clear first of all to all of you what we've done with it. And then secondly also the calculation. First, the application of lens maker's formula individually to that water layer which is acting like a plano-convex lens, and to the glass lens which is obviously a convexo-convex lens, convexo-concave lens. So this type of question has appeared in IIT-JEE papers on multiple times. The values might be different, I don't remember the exact values, but the exact same concept has been used in multiple JEE questions previously. Let's pick up another question based on previous year IIT example, based on the same concept. So the next example is like this, that we take a symmetric biconvex lens made of glass. So a thin symmetric biconvex glass lens, focal length focal length, let us say whatever 1.8 meters, and refractive index of glass p by 2 is cut by a plane perpendicular to its axis into two identical plano-convex lenses, which are then placed as below. In the diagram below, we are showing what we are doing is we are first cutting that lens into two plano-convex lenses. Then we are flipping those plano-convex lenses and placing them like this. And in between, we are putting water. This is a thin water layer. Refractive index of water is 4 by 3. So now on this combination, if I have light incident from infinity like this, you have to find the position of the image. That means you have to find the focal length. So position of image from the incident. So this is the data given to me in the question above, and this is the calculation we have to do now. So just try this out. Ganesh, come again. With 35.4, 5.4. And real or virtual? Okay. So hope you have substituted the focal length of the water lens with proper sign. Okay. Yeah, Somadip, I'll just verify your answer also. Ganesh, just wait a minute, I'll verify your answer. Yeah, it's correct. Both of you have got the correct answer. Samyak, your answer is correct. Somadeep and Manish, you answered the correct obviously. So here what you will see is the calculation can actually be done very easily. If you just, so first I'll tell you how I could have done it with a minimum amount of calculation. Of course, keeping in mind that I have a lot of previous experience in solving this. Okay. So I know that for refractive index of glass equal to 1.5, any symmetric lens, it has the radius equal to magnitude of the focal length. So if you know this, then it's very nice. Otherwise, you have to do one calculation more. So here I will know that the radius is already how much? It was 1.8 meters or 180 centimeters. So each side had a radius of 1.8 centimeters. Now I'll also know that for cutting a symmetric lens into plano-convex, or for that matter, it could also be plano-concave if it was a symmetric biconcave lens. The focal length becomes such that f prime becomes 2 times f. So what is happening is, therefore, the two plano-convex glass lenses in this example each have a focal length f1 with my sign convention, which will be equal to plus of 3.6 meters or plus 360 centimeters. Correct? Okay. Now the only thing we have to do a calculation for is the water lens. Okay. Now the water layer in between, that acts like a symmetric biconcave lens. That acts like a lens which is like this, made of water, but both sides having radius. We already saw 180 centimeters, and refractive index of water 4/3. So it acts like a focal length 1 upon f2, let us say, is 4/3 minus 1 by r1 minus 1 by r2. So this will become 1/3 of minus 2 by 1.8. So 1 by f2 become how much now? Minus 1 by 2.7. So this is the power of the water lens. So the water lens is acting like 2.7 meter focal length diverging lens. If I don't bring sign into, or with sign, it is f2 with sign is minus 2.7, or we can say that the diverging lens. Now you look at the combination. So the combination is basically like your glass lens of focal length f1, which you calculated above, plus a water lens placed in contact with it, plus again another glass lens. And interestingly, actually, the combination of the two glass lenses will give you the original glass lens. 1 by f1 plus 1 by f1 will give you 1 upon f of the original glass lens. So the equivalent focal length here will be such that it is 1 by f1 plus 1 by f2 plus 1 by 1. So it is nothing but plus 1 by 3.6 minus 1 by 2.7 plus 1 by 3.6. it is 1 upon 1.8 minus 1 upon 2.7. So you can take 90 centimeters common. Just write this as 1 by 2 minus 1 by 3. So the equivalent focal length becomes positive of 6 into 0.9. So positive of 5.4. So that means the combination will act like a converging lens. Of focal length 5.2. Okay, so that means in my original ray diagram, this is what should happen. These rays should emerge out converging like this now. So you can see I was able to do this question with minimum of first because I used a lot of results which I kind of memorized from before. But in case I have not memorized those results, it will take me a little bit more time, but I can still figure this out because I will have to first calculate this, that how much the radius is. So for this, I'll have to use the formula 1 upon focal length of the glass lens is refractive index of glass minus 1. 1 by R1, which I'll write as 1 by plus of some radius, minus 1 by R2, which I'll write minus of that same radius. So from this, I will have to first work out that the radius is 180 centimeters or 1.8 meters. I have to work this out first. Then again, I'll have to use this. Okay. From this, I'll have to work out that 1 by F prime or F1 or whatever for the plano-convex lens, this one, is refractive index of glass minus 1 into, suppose I'm talking about plano-convex. So this will be plane side on one side and convex on the other side. So minus R. So from this, I'll have to work out that okay, F1 comes out to be plus of 360 centimeters. So extra steps will come in. And then this, so anyway, I'll have to do because the refractive index from these. So that's why it is useful to solve a lot of questions so that these little tricks can be, like they'll become rules of thumb for you while solving. So just remember this special case that symmetric lens hai or glass ka refractive index 1.5 hai. So the radius is magnitude is the same as the magnitude of focal length. Then that symmetric lens is cut. So the two plano lenses that you get, they will be of same type of focal length. Then if it was converging earlier, it will remain converging. If it was diverging earlier, it will remain diverging. But the focal length will become double, or the power will become half. And then this. Okay, so I will just take you through all the calculations once more. Okay, so hope everybody else is clear with this full set of calculations. So these were the individual lenses how we got. The two plano-convex lenses focal lengths came out to be 360 centimeters or plus 3.6 meters each. And the in-between water layer, which now acts like a biconcave symmetric lens, that will act like a diverging lens of focal length 2.7 meters. So now the combination of the three. So for the combination of two, if we have a formula, 1 upon F equivalent is 1 by F1 plus 1 by F2. If we have 3 or 4 or any number of thin lenses in contact, we can just extend their formula. So the equivalent power becomes the summation of the power of the individual lenses. But remember the focal lengths or the powers, have to be substituted with their signs because we are using the Cartesian sign convention. So everything is with Cartesian sign. So again, this question is based on an actual IIT question. Only the values were different. I don't remember what the radii and all that. But this exact same concept, symmetric biconvex lens is first cut. Then the two plano-convex lenses are placed reversed like that, and some other liquid is placed in between. So if I remember correctly, this was, I think, an integer answer type question in one of the advanced papers. Oh, so now we come to the final part of this, equivalent sort of formula, that how we can replace a combination into an equivalent single element system. Yeah. System which has a combination of optical instruments and convert that into a single equivalent optical instrument. So now next thing you look at, the last of these formulas, equivalent formulas, combination of a thin lens and a spherical mirror. And actually we can include plane mirror also as an exceptional case of spherical mirror with radius tending to infinity. That's all in contact. In contact. So it acts like, this combination acts like an equivalent single mirror. So for example, if I take some kind of a glass lens, just for example, I've taken this, and some kind of a spherical mirror, like this. And then I make light incident parallel to the principal axis. So depending on what happens here, the light might, after reflection, the reflected rays might come like this, or the reflected rays might come diverging out and form an image behind. But the system acts like a equivalent mirror. We can say this will be equivalent to single mirror of some equivalent focal length. So right now, this is a spherical mirror which has, let's say, focal length denoted by F2 because it's a mirror, and this one is a thin lens with the focal length denoted by the symbol FN, FL and FM, where we will use the standard sign convention for FL and FM. So first I'll give you the formula, then we do the derivation. Now, 1 upon F equivalent will be minus 2 times 1 upon focal length of the lens plus 1 upon focal length of the lens. Just note down this formula first and then we will look at the derivation of this. In fact, the derivation of this itself is like an application. Because we can say that we want to prove this formula now. So we'll just take any arbitrary lens and mirror and show that rays incident parallel like this will form an image at a position which is given by this kind of formula. That position will become the equivalent focal length. Okay, so Once you've written down this formula, let's directly jump into a numerical example and do this, do that. Then we can look at the general proof later. So for example, if we have a converging lens of focal length equal to, let us say, 60 centimeters. And we are placing that in contact with a convex mirror like this. Which has a radius, let us say, of whatever, 180 centimeters. Now we want to find the position of the image for rays parallel to the principal axis. So find the position of the image for parallel incident rays from very far. So what you do, what I want you to do here is, once do this question by fundamentals. That is, the rays are suffering refraction by the lens, then reflection by the mirror, then again refraction by the lens. So three events like that. Once going to the lens, then once reflected by the mirror, then again refracted by the lens. So once solve it by that method, and then once solve it by the direct formula I've given you above, and that will show you how that formula is valid. Then we can later use the similar method to actually come up with the proof of this formula. Okay. But remember, both this formula and your own application also of the fundamental event by event method, everything has to be done by sign convention. No, the formula will come out to be this only. I'll show you that. The minus sign comes because ultimately the light reverses direction because of the mirror. But remember, we are going to use the common sign convention for both the lens and mirror. Okay, so we'll prove it in this example only. So this system will act now. Remember that F equivalent will become an equivalent mirror, not an equivalent lens. It will become an equivalent mirror. Okay, so we have to treat it like a mirror of equivalent focal length that much. So anyway, don't worry, we'll show it. So just do what I'm saying over here. Try this out. Let first try this question by fundamental method, event by event, okay. And then do it by this formula. तो ठीक है, वो इसमें भी आ जाएगा फिर virtually. So let's do this one event at a time. From fundamental method. So what is happening is the first event is refraction through the lens. It is very easy. The rays are parallel to the principal axis. So the image I1 should be formed over here. So if this is my V1, so first event, parallel rays incident on the lens. So event is at the focal position of lens. So V1 with my sign convention, I'll get as positive of 60 centimeters. That was the lens's focal length. So this is my first event. this side is positive, this side is negative. Now let's come to the second event. As far as the second event is concerned, now the job of the lens is over, and the rays coming out of the lens, which are like this, so they would have converged to this point I1, but these rays are now intercepted by my mirror. This is what is happening. So these rays getting intercepted by the mirror. So let us see where the image the mirror is forming. Okay, so for the second event, the reflection by the mirror. So again, I'll take this side as positive and this side as negative. So the center of curvature of the mirror is somewhere here. So I'll have 1 by V, which is, let's say, V2, plus 1 by U, which will become plus 60 from above, will be equal to 2 by R, which is, I think it was 180 if I'm not mistaken. Plus 180. So for the mirror, you can see that I1 becomes the object. And in this case, it's a virtual object. So let's see what we're getting for this. So we're getting 1 by V2 is equal to 1 by 90 minus 1 by 60. So we are getting V2 as minus 180. Correct? So that means it's giving me a real image. The second event is giving me a real image. For whatever reason, this is what shifted here, I don't know why. Fine. Back in place. Okay, so this is the result as predicted by my formula. As predicted by my formula, this is what these rays give me my I2 over here. But this apparently I'm getting as 180 centimeters. Just check my calculation as I'm going along. Yes, some of them I'm correct so far. Now what is happening? This is not the final image. Once more you are getting reflected by the lens. So you have your third event. Now this is where it becomes a little tricky. Because in the third event, this is what is happening. Unfortunately, my internet connection went out for a second. Hope you are getting me now. Yeah, it seems audio and video are both there with you and whiteboard also. So the third event, क्या हो रहा है? Mirror से जो reflected rays आ रहे हैं, वो ऐसे इसमें incident है. So my I2 is becoming a virtual object for the lens. But remember, this time light is coming from this side for the lens. Light is coming from this side. So its focal position is not here for the lens because it's a converging lens. Okay. So we'll continue with the same sign convention. We don't want to change the sign convention. We keep this side as negative, but this side is positive. But this time the real focus will mean that the focal length of the lens we have to write with a minus sign because the light is coming from the positive side. So the real focus is on the negative side, and that is how much minus 67. But if it was going from this side to that side, then the focal position is here. But if light is coming from that side to this side, the V2's sign also. So you can see that I2 is becoming a virtual object. So I'll substitute U as V2, which we got as minus of 180 with the proper sign. So you can see that this is the sign here is reflecting the fact that it's a virtual object. Okay. And I3 will become the final image. So wherever that final image is, that will become my equivalent focal length for the system, because the original incident rays were like this. So now let's use the UV formula for the lens for the third event. So 1 by V, that is 1 upon F equivalent, minus 1 by U, so that is minus 1 is equal to 1 by F, which will come with a minus sign. So we should be getting this, that 1 upon F equivalent is minus 1 by 60 minus 1 by 180. So that is 3 plus 1 minus sign divided by 180. So I should be getting the equivalent focal length of the combination as minus of 180 by 4. So that is how much? Okay. So just check my calculation, people, once, but barring any calculation error, I should be getting this as correct. Obviously, it will become evident in just a moment, because I'll also do it by the distinct formula. So this is a very critical step here, people. Make sure that you understood this, that why, even though it is a converging lens, this time I have taken the focal length position here and not there, because the light is coming from the left side. So the real focus point is on the, light is coming from the right side, okay, or from the positive side. So the real focal position is on the left side or the negative side. And when we do the derivation also, this thing is one of the reasons why we get that final formula as minus 2 by FL plus 1 by FL. Okay, so third event is giving me this. Okay, now let's do this by the formula method. So if I were going by the formula method, now obviously in exam you will go by the formula method because it's much faster. You will replace the combination of this lens plus mirror as an equivalent mirror. And that equivalent mirror will have a focal length such that 1 upon F equivalent is equal to minus 2 upon focal length of the lens plus 1 upon focal length of the mirror. Now this was a converging lens of focal length 60 centimeters, and this was a convex mirror of radius 180 centimeters. So using the sign convention that this side is negative and this side is positive, I will now replace in this formula this as positive 60, because here I am still assuming light is coming from this side, so the focal position is on that side, plus this will become 1 upon minus, 1 upon plus 90. Q plus 90 hoga, because see, with the proper sign convention, the radius is on the positive side. So this will show us that for the mirror with sign convention, the focal position of the mirror is somewhere here. let's do this calculation now. Is minus 1 by 30 plus 1 by 90. So we should be getting this as minus 3 plus 1 upon 90. So we are getting the equivalent focal length as minus 45 centimeters. So that means the combination should be acting like a converging mirror or like a concave mirror of focal length 45 centimeters. So this combination should be doing the same job as this thing. This, which means that light incident here will give you a real final image at 45. So you get a real image at 45 centimeters in front of the pole. The same thing happens. Okay, so in some books, etc., this is given in different forms and all that. They say that add the power of the lens twice and the power of the mirror once, but they don't, for some reason, I don't know, very few books give it with the proper sign convention. But if you're consistent with the Cartesian sign convention, you'll be able to use this formula in this form, that it is minus 2 by FL plus 1 by FL. So whether it is a combination of, convex lens and concave mirror, or for that matter, even convex lens and plane mirror. So plane mirror mein kya ho jayega? Focal length of the mirror will become infinity. So this term will just become 0. So, if you have something like this, you have a lens like this with a plane mirror over here. This will now act like a mirror like this, which has a focal length of just minus 2 by f. 1 upon f equivalent is just minus 2 by f. That kind of. So you can even go back to that question we did with a plane mirror with the two lenses kept on top of that, and we recalculated by now first reducing the combination of the water and the glass lens as a lens, and then the combination of the lens and the plane mirror itself as an equivalent plane. Then you'll see you'll have to place the point object at the center of curvature of the equivalent plane mirror to get the position of the source coinciding with the object. So just like we've done this with numerical values, you can do a general derivation to put the formula. You can do that as part of your homework. So part of your homework will be the general formula proof. But when you're doing the proof, you just have to be mindful of the step that we discussed. The third event, that is the refraction of the lens, refraction by the lens the second time it happens, it gets reversed. The light is now coming from the positive side. So whatever focal length is written for the first reflection, for the second refraction, it should be replaced with a minus sign. So for example, if it is a converging lens, like in this case, for the first refraction, the focal length of the lens comes with a plus sign, but for the second one, it comes with a minus sign. Similarly, if it was a diverging lens, for the first refraction, the focal length would come with a negative sign. For the second refraction, it should come with a positive sign. So use this, and also use this to a problem, also part of your homework. Solve a problem which is like this. You will find this problem in HC Verma. I'll also be sending an additional set of problems where we have silvered one side of a convex. So this side is silvered. So now what is the equivalent focal length? So we can use this formula. Now the silvered side is just basically a mirror of the radius of curvature, which is the radius of curvature of that side of the lens. So for example, again, if R1 and R2 were 12 and 18 centimeters, you can see that you silvered the side which is having 12 centimeter radius. So that side will now act like a mirror which is of radius 18 centimeters or focal length 9 centimeter with the proper sign minus or plus. Okay. So with this, people, we come to a conclusion of today's lecture. And very critical lecture in terms of problem solving. So make sure you are, yes, the sign convention you can see in that sense are successively chosen. Okay. And remember that whatever equivalent focal length you're getting the formula, that has to be treated as the focal length of an equivalent mirror, not the focal length of an equivalent lens. No, so lens and mirror have that difference. If you have equivalent focal length as negative and you're talking about a mirror, that means it's acting like a converging mirror. Okay, whereas if you were talking about a lens, it would be acting like a diverging lens. So you have to be careful about the interpretation of that. So if you just follow the exact language of the the definition which I have given, and also the exact method in which I have solved this question, both the first time and the second time, to prove why your equivalent focal length is coming out to be 45 centimeters like that, you will get what I'm talking about. You should not have any difficulty. And of course, while doing the questions or the derivation, if you have difficulty, you can always get back to me. I will help you out over WhatsApp or whatever. So that's it for today's class, people. Very critical class in terms of the JEE advanced type of problems. Okay, your JEE advanced problems will have the maximum application of these kind of concepts that we are discussing.